Hi, everybody, and welcome to what I believe to be our last recorded video of the semester. Anyway, with that celebration done, um, we're getting on to some new and interesting integrals today. We're going to start by finding volumes using slices. So even though we are in single variable calculus, we're going to get into the third dimension today. We're going volume with slices early on. Eventually, we're going to do volumes of revolution using the shell and the washer method, which are going to be great too. Um, but yeah, we're going 3D. And the first things first, we need to figure out how to find volumes using slices, using only one variable. The key to this is that we're going to need to pay attention to cross-sectional area. Um, I mean, if we take a look down here at the sphere that's down there, you can notice that there is a red cross-section circle that's highlighted. The idea is, hopefully, we should be able to calculate the volume by adding up a bunch of thin slices as we slice through the sphere. And to make this a little bit more concrete, oh my gosh. All right, we'll go big real quick. All right. So, I have in my hand a normal deck of cards. Pick a card, any card. Anyways, the idea is if we wanted to find the volume of this deck of cards, I mean, one way to do it, if it's just a nice rectangular prism, we can go length times width times height and, get a nice volume for the rectangular prism. But in this section, we're going to be calculating the areas that are a little bit weirder. But even if I were to like fan out the cards like this, I should do it in a somewhat continuous manner. All right, so even if we have something that's not a rectangular prism, we kind of know intuitively that the volume of this deck hasn't changed. And so one strategy for getting at the volume of this deck, even if it's in a strange configuration like this, is to look at the volume of one card. If there are 52 cards in the deck and we find the volume of one card, then theoretically, we found the volume of the deck. How would you find the volume of one card? Well, on this side, the Five of Hearts has a pretty significant length, a pretty significant width, but it's got like basically no depth. And this really, really skinny side, think of that as our dx side. That is like the tiny little differential side. Whereas we're going to calculate cross-sectional area based on the cross-section that we have. So sometimes we're going to have cross-sections that look like circles. For a deck of cards, the cross-section would look like rectangles. But the idea is we could calculate the entire volume of this deck by going card by card by card, slicing the deck. And this one has a constant cross-sectional area, which is kind of boring. But, if we go back into the example that we're just looking at with the sphere, hopefully this is, yeah, I'm screen sharing. Let me see. Okay, great. We're screen sharing the right one. Yeah, we'll see that this cross-sectional area changes. At the beginning, you start slicing the sphere or perpendicular to the x-axis, you would cut off like a tiny little dot off of the end. Um, maybe I could draw a little circle there. That could be like a tiny little dot. And then the next one, you get a circle that looks like this. And then maybe as you get towards the middle, you're cutting an even bigger circular cross section. Goodness. All right. Seriously, the screen shifted on that one. That's oof. Um, but you could get a bigger cross section. The idea is that all of these cross sections will be circles, but that area might change throughout it. But the idea is if we cut this into thin slices and added them all up, we should get the volume. So that's what we're going to do. I'm going to erase that. I'm going to erase that. And yeah, in this one, we are orienting ourselves perpendicular to the x-axis. And so we're going to use that as a guide. Overall, the integral is going to look like, well, volume equals the integral from, for right now, I'll just go a to b. These are going to be x values that we're going to figure out shortly. And we need to come up with some kind of function that gives us cross-sectional area. Yeah. And that cross-sectional area will be dependent on the x value that we're at. So this one is our, our x value. And then we'll go dx. And so, yeah, the idea here is we're going to be marching along the x-axis, hopefully from some smaller x values up to larger x values, and we integrate over this entire sphere. Okay, so what they've given us in this problem is going to give us a little bit of a head start. They are showing us that the square root of r squared minus x squared is that tiny little radius. The idea being that the sphere has a radius of little r. And as we march along from the beginning of the sphere all the way to the end, this x value is going to change. So we've got this right triangle where the leg is going to continue to change. The value of r shouldn't change. That's going to be a sphere, or it's the radius of the sphere. But this also will change dependent on this radius. So this little r squared minus x squared, I would like to call this big R. And let's give it a green. And if I wanted to, continue to write this volume, we could get at the cross-sectional area by going pi r squared, because that is the, cross-sectional area of a circle, or that's the area of a circle. Let me go ahead and write that for pi big R squared. And now I'm tempted to make this red instead of green. I know I just changed my mind. But yeah, that's a good cross-sectional area. We're still going to be working with dx. And how could we tell how far we're going from the left to the right? Well, since this is a sphere of radius r, we would be all the way out here at negative r on one end, and we would be all the way to positive r on the other end as far as the x-axis goes. And so negative r up to r could be something that's useful. Remembering the symmetry stuff that we talked about on Monday, since this is, a sphere that is symmetric on both sides, going out to negative r or going out to positive r, we could do 2 times this hemisphere if we wanted to do that and get rid of the negative r and make that a 0 kind of a thing. For right now, I think this is already complicated enough. So if we trust this as the radius of our circle, let's go ahead and just keep moving forward with this. Little r, little r. I'm going to throw pi out in front. And the r squared will turn into the square root of little r squared minus x squared. And then we've got that squared, and then we've got dx. So now This is a little bit confusing because we're treating little r as a constant rather than a variable. It's weird to see letters there, but if it helps, just imagine that r is like 4 or something. But yeah, we should be able to integrate this and find a solution. Hopefully, we find the correct formula for the volume of the sphere. I'm going to leave pi. I'm going to do this, negative r to positive r. And then this nicely turns into r squared minus x squared dx. Let's go ahead and bring this all the way up. And then keep going. Now let's take an antiderivative. I negative r up to r. We've got, oh, no. We're just going to do the antiderivative here. Sorry. Antiderivative of r squared is xr squared. Antiderivative of minus x squared is negative 1/3 x cubed. Negative r to r. Okay. So let's go ahead and substitute in r's where we see them. We've got pi. Here we've got r cubed minus 1/3 r cubed for the first thing that we plug in. And then we're subtracting and we're putting in negative r. So we've got negative r cubed and then plus 1/3 r cubed when we put in the negative r. And yeah, this is what I was saying earlier, that like this ends up just being 2 times r cubed minus 1/3 r cubed. Okay. And actually, r cubed minus 1/3 r cubed is just 2/3 r cubed. And so in the end, we get 4/3 pi r cubed, which is the volume for a sphere. So we just did calculus to do that. And we actually added up a bunch of little cross sections of the sphere to get the entire volume. And I hope you appreciate that. This is a powerful thing. This is pretty cool. I suppose I did a GeoGebra thing and we could look at it. Okay. So here I've got a sphere of radius 3. This is going out to -3 on the x-axis to +3. And if I, slide this back, this is how we were taking the area. We were cutting a bunch of cross sections. Now, imagine that circle being filled in and, each one of those is kind of a tiny volume that we're adding up to get the overall volume. So pretty cool. That's what we just did. All right, so let's go back here. Moving on to the next one. Here we've got a pyramid of height h, whose base is a square of side length s. And I just drew this. I was practicing this one earlier. This is the diagram that they gave us in the book. Find the volume of a pyramid of height h. Gotcha. So looking at this, we are actually going to be integrating cross-sectional areas that are perpendicular to the y-axis now. So we're going to set this one up as a dy. In the most general sense, we're going to go from some starting point to some ending point. We're going to create an area function based on y, and we're going to go dy. Okay. Now, we can take this, step by step. We don't have to jump right to the end. In the y direction, what values are we going in between? Well, if y is this variable, if it's how high up this red cross-sectional square is, we could go from y = 0, and we would be up at the very tippy top of the pyramid, and we can go all the way down to h, which would be the total height of the pyramid, and we'd be going at the very bottom. So I would say we're going to integrate from 0 to h on this one. Those are all of the values that y could take on. A of y is a little bit ambitious right now. What I see is an area function in terms of x. So I'm going to go ahead and write x squared for the cross-sectional area of that square, knowing that we're going to need to turn it into y. But that should be possible. If we want to turn that x squared into something in terms of y, we're going to have to figure out how slanty this thing is. And that's why I had these lines drawn earlier when I practiced. Um, we've got a pair of similar triangles. There's the one that between y and x, and here's the one between s and h. Since they're on the same, object, those things are similar. And that means that we could make a proportion. I'm going to go ahead and do that over here. Let's say y over x is equal to h over s, as the ratio of the side lengths between those right triangles. Then we want to solve, we want to solve for x. So I didn't do a very good job of this. X times h equals y times s, just cross multiplying through that proportion. Okay, then x equals y times s over h. So that is actually a good substitution that we'll be able to put in over here. And then we'd have everything in terms of y. So we've got ys over h squared dy. I think we can fit one more integral in. For the next one, I'm going to go ahead and square everything on the inside. I'm going to pull the constants out front. S squared over h squared. You come out front. And then y squared, you can chill on the inside of the integral. Okay. Then we are in business. We're going to be able to integrate this s squared, h squared, coming along. We're going to go ahead and integrate this time. So antiderivative of y squared becomes 1/3 y cubed. We are evaluating that at h and at 0. So we've got the s squared over h squared times 1/3 h cubed. And if I was going to do the 0, that part would just, die away. But anyways, we should be able to multiply this together now. I've got h cubed on top and h squared on bottom. So that works out to just being an h that's left over. So in the end, I've got 1/3, s squared, and then h at the end. So our volume is 1/3 s squared h. And that's true for these pyramids. They are 1/3 the volume of their corresponding prism. So yeah, doing s squared for the area of the base and then times the height, this is the correct, geometric formula for the area. And I guess I made another GeoGebra thing. Ooh. All right, so there's, a pyramid with respect to the corresponding prism that it would fit in, and you could actually fit 3 of these pyramids inside of that prism, and it would work nicely. I didn't remember to bring my blocks to show you, but it works out. Oh, all right, we didn't want to change that. I wanted to change this. Ooh. Okay, no worries. I wanted to change. Okay, anyways. Yeah, GeoGebra things. It's fine. We did the important part here. Okay, let's keep going. Next one. we've got the curved wedge. We're finding the volume of cheese. Okay, we've got a right circular cylinder, the XY plane, and a second plane passing through the Y-axis at an angle of 45 degrees to the XY plane as shown. The cylinder's axis in the Z-axis, is the Z-axis, and it has a radius of 2. Okay, so what's the volume of the wedge? Gotcha. We are going to try to calculate the volume of this wedge using rectangular cross sections. This is, not the only way that we calculate this volume, but it's a good way. So we're imagining cutting out a bunch of rectangular prisms and chopping from x equals 0 at the start all the way out to x equals 2, where this cylinder ends. So let's go ahead and start making our integral. I think that we can go from 0 to 2, and we've got the dx as our differential. And now we need to figure out the area of that rectangle. Area of a rectangle is base times the height. How might you figure out how long this length is without it just being shown to you? Well, at this point, it is just being shown to you. But if we were going to go from this function over here to this function over here, we are on the right half plane. And so if you wanted to describe that semicircle using two functions of x, you would need to do the top portion of that semicircle as the square root of 4 minus x squared. And then you need to do the bottom portion, y equals negative 4x, or square root of 4 minus x squared. So you get the negative version on bottom. And then you would be taking the difference between those to get this distance. So it's the top minus the bottom function gives you 2 times the top function, basically. That distance is just twice. So if we're calculating the area of the rectangle, one of these, since this is at a 45-degree angle and we're moving along this way, if we call this value x, then this height is also x as well. So we could go x there for, let's say, the length. And then the width of the rectangle is 2 times the square root of 4 minus x squared. And that should be a good formula for the area of a cross section, because we just have a rectangle this time. It's not too fancy. So yeah, if we set up this integral, we might initially wonder how we're supposed to solve this. If we think back to Monday, this is a U substitution problem. So let's go ahead and do that. Do I have some room? Sure. All right. U, we'll make that the inside function. So U equals 4 minus x squared du equals negative 2x dx, and negative 1/2 du equals x dx when we divide both sides by negative 2. So we should be able to substitute out x dx and get a du, and then do the rest of it as 2 times the square root of u. And now we've got, a question. Do we want to keep, do we want to work with x, or do we want to work with bounds of u? I'm going to go ahead and let's change these bounds into u bounds instead of x bounds. So up here, we've got x equals 2 and x equals 0. And I want to turn this into u bounds. So I'm going to throw in, x equals 0 into here. If I throw in 0 there, then 0 turns into u equals 4. If I throw in 2 into here, u turns into 0. Oh, geez. So this is a little bit weird, but we got to make these match up. Since our bottom bound turned into, went from 0 and now turned into 4, we've got to write that still down at the bottom. X equals 0 corresponds to u equals 4, and u equals 0 corresponded to x equals 2. And now we've got a definite interval that's totally in terms of u, and it's going to be easier to solve, but it's a little bit weird. I think probably one thing that would help is reversing the order of integration so that now we go from 0 to 4. And in order to do that well, we need to put this negative sign out front as we exchange the order of integration. And then I think we should be able to do this. Yeah, the antiderivative of u to the 1/2 power is u to the 3/2 power. And then we also need to divide by that power. So dividing by 3/2 looks like multiplying by 2/3. And then we've got a 4 and a 0. So yeah, we should be able to go 4/3 times 4 to the 3/2 power. And we should be able to, oh, that's what happened. I forgot. Okay. I'm sorry. I messed up with the negative here. When I substituted in x dx, I neglected to put a negative sign right here in with that du. That was my bad. And then when I changed the order of integration, this negative sign should go away. That's my bad. I was wondering why we were getting a negative volume at the end of this. But yeah, I forgot to put this negative sign in here. I also forgot to put in the 1/2 along with it. What am I doing? Oh my goodness. All right. I'm going to turn that into a 1/2 and throw a negative sign out there. This still needs a 1/2. Sorry. This then needs a 1/2. And we need to multiply by this by 1/2 now. Okay. So I think we're back on track. I just, messed that up for a while. Okay. We should have 2/3. 4 to the 3/2 means take the square root of 4 and get 2, and then cube it to get 8. And so this is 16/3 in the end, which I believe is correct as the volume of that wedge. Sorry for the confusion over the negative sign, but I think that's pretty good. Let's go ahead and move on to the next one. The summary for this section is to find the volume using cross sections. You develop a formula for the area of a cross section and then integrate in the perpendicular direction. So on these ones, we had cross sections that were perpendicular to the x-axis. Here's one that's perpendicular to the x-axis. This cross section, this red square, was perpendicular to the y-axis, and that's why we did dy on this one. Okay. The next one is finding volumes using cylindrical shells and washers. So volumes of revolution. The idea being that based on this little leaf pattern, here we're trying to find the volume of a solid formed by revolving this leaf region around the y-axis. So on the top of this is y equals the square root of x. On the bottom of this is y equals x squared. What I'm trying to do in this first one is take a big picture overview and show you how these strategies relate to each other. One of them is going to be a shell strategy. The other one we're going to call a washer strategy. And it totally depends on how you're orienting your line segment compared to the axis of rotation. So here, maybe I'll do this. Uh, if you have a line segment and you're orienting it parallel to the axis of rotation, if you rotate one finger around the other, you're tracing out a cylinder, a cylindrical shell with your one finger as it goes around. Let me go ahead and it's going to be clearer in GeoGebra if I do this right. Um, okay, so if I rotate this thing around the y-axis, let's watch what happens. It's rotating, rotating, and there's that little line segment that's getting copied over and over. Nice. So we did one rotation, and this is what we're going to call a cylindrical shell. So notice how cool that is. If we wanted to change the placement of our cross section thing, our line segment, we could go around and we can make another cylindrical shell. This one's smaller since that line segment's smaller and this thing's closer to the axis of rotation. But the idea is if we were going to continue to do this at different values, we would continue to make more and more cylindrical shells. And if we did it all the way through, theoretically, we could do enough cylindrical shells to calculate the entire volume of this volume of revolution. So, yikes. Here is the volume that we're trying to calculate, and those are how the cylindrical shells are related to it. So that's pretty cool. That is when the line segment is perpendicular to the axis of rotation. Okay, so now if I reset things and get those away, and I get, oh, well, yeah, we don't want that. If we change it into washer mode, now we've got a line segment that's perpendicular to the axis of rotation. Here we're going to still rotate, but now the shape that we're going to make, looks like a washer. So, at least, in terms of the hardware washers, you can put a screw through that and, yeah, be good. So there's a washer. If we wanted to go a little bit farther out, we totally could and do this again to make a different size washer. But the idea is if we made these washers at every step of the way, in this case, we're integrating with respect to y because all of these cross sections are perpendicular to the y-axis. But again, if we were to make a bunch of these cross sections, the idea is that we would get this entire volume that's bounded above by the square root of x, bounded below by x squared. And this time we could do it with washers. So I tried to pick this first example as one that we could do either way. And both of these methods look good. Let's go ahead and try to look at the particulars of this. All right. So when we're doing this, we're going to be doing this, if we're rotating around this way and our line segment is parallel to that axis of rotation, we're making a shell. If we were to rotate this way around the x-axis, then we would be making washers. For this orientation, if we set up our line segment horizontally and we rotate around the y-axis, we're making washers. If we were to rotate around the x-axis, we'd be making shells. And so right now, these integrals that I've set up aren't actually integrals for the entire volume. These are just integrals that give you the area in between these two curves, but that's important because that's the cross-sectional area that we're looking for. And we're going to be able to utilize that to create shells or washers depending on which strategy we want to go with. So, okay, this is my best sketch of what we've got going on. Um, and I want to examine how these cross-sectional areas relate to the line segments that we've highlighted. So here's our little DX line segment. If we rotate it around, we make a cylinder. And here's that cylindrical shell. Notice that, it's got a circular shape and the radius is, we're going to call it little r. We're going to call the height of the cylindrical shell h. And if we unwrap the cylindrical shell and put it down as a rectangle, um, the cool thing about this is that, it's the lateral surface area of a cylinder. The area of this shell is 2 pi r because 2 pi r is the circumference of the circle, and that's how wide this rectangle is. And then we multiply that times the height, which is just the top function minus the bottom function kind of thing. So overall, the area of this cylindrical shell cross section is 2 pi r h. And the idea is that is the cross section that we're going to try to build in to our integral. So as we do this volume of revolution integral, we're going to do it based off of the area of a cylindrical shell. So we've got the 2 and we've got the pi. In this case, the radius of our cylindrical shell is just the x value because we're centering this on the y-axis for our rotation. So we're going from the center of our rotation all the way out to wherever we're making the cylindrical shell. So r is equal to x in this scenario. So that's r. And then we're figuring out the height of each of these shells by doing the top function minus the bottom function. We're doing the square root of x minus x squared. And so based on the area formula for a cylindrical shell, we've set up this integral that if we solve it, we're actually going to get the volume of that entire shape. And so we could look at how this will shake out. We could bring that 2 pi out to the front. We can multiply these together so that, they're nicer to work with before we actually take antiderivatives. Here we take antiderivatives, we substitute in 1 and 0, and eventually we get 3/10 pi for our volume. But the main thing that I want you to focus in on now is how we set this up. It's based on the volume formula for a cylindrical shell. This is 2 times pi times the radius times the height. And that's how we create the integrand for, the cylindrical shell method. On the other hand, the washer method is based off of, this washer shape. And it's like a couple of concentric circles. On this one, we're going to focus in on an outer radius and an inner radius so that we can make some circles and cut out a little circle from a bigger circle's area. So in this case, we're doing it on the formula for the area of a circle. If we did pi big R squared, we would get the area of the big circle. And if we subtract off pi little r squared, we're subtracting off this little circle on the inside. So this is the formula for, the area of this washer. If you want to condense things and only write pi once, you can write it as pi times the big radius squared minus the small radius squared. And if we're working with the functions that we were looking up above, here we're thinking about, okay, what's the function that has the biggest y values? And that's actually y equals x squared on this one. I might go ahead and actually write on this one. So let's pick a color that I haven't used. Get out of here. Let's go green. So yeah, this function formerly known as y equals x squared. If we solve this for x, this is x equals the square root of y. We're in the positive part of this, so that's all good. And on the other one, I don't know. We've already used a bunch of the colors, and the other ones aren't going to show up. Let's use red. This one, formerly known as y equals the square root of x. If we square both sides, we would get y squared is equal to x. This one is giving us our inner radius, and this one is giving us our outer radius. Because the outer radius is the one that's farther away from the y-axis in the positive direction, and the inner radius is the one that's closer to this axis of rotation. So when we come down here, you're going to see the square root of y acting as the outer radius and y squared acting as the inner radius. And then, we've got this whole thing. We've got, the area of a circle. If it's just a disk, it's just pi r squared. No big deal. When we've got a washer, we've got to worry about the inner radius and outer radius, but this is working well. And notice that once we square those things and we take an antiderivative and we use the fundamental theorem of calculus part 2, we get the same answer as what we did when we did cylindrical shells. So both of these ways are valuable. And, if we set them up correctly and implement them correctly, they should come up with the right answer. Sometimes one of these is going to be way easier than the other to set up, depending on the functions that we're given and the radius that we're trying to rotate around. But again, this should feel like a level up. It should feel like something that we're able to do that's pretty cool. We're able to find the volumes of things that are very weirdly shaped. At least in this section, as long as they have some rotational symmetry that we can utilize. So yeah, just an overview again, the shell method has the line segment parallel to the axis of rotation, and the disk and washer method have a line segment perpendicular to the axis of rotation. And so, yeah, I mean, this is the book's method. When it reverts to the disk method, that means it doesn't have a hole in the middle. Washers have a hole in the middle, so an inner and an outer radius kind of a thing. So that's pretty cool. I think that we have time for maybe one example. And then I think we can be close to being done. Yeah, okay. I think that's probably where we need to be. All right, in this example 4, we're going to use the disk method to find the volume of this paraboloid if it was solid. Okay. So yeah, it's this area that we're rotating around the y-axis, and it gives us that solid paraboloid. Cool. First we need to decide whether this is the disk or the shell method. And the way that we're oriented right now, the axis of rotation is vertical, but our line segment is horizontal. That means we're perpendicular, and that means that we're doing a disk or a shell. Or sorry, a disk or a washer. And in this case, since our line segment goes all the way to the axis of rotation, there's no inner radius that we need to worry about, and we are definitely doing the disk method. And since, our cross-sectional area is going to be a circle each time, the area of that circle is pi r squared. So that's what we're, expecting to see. You know, over all of this, we're going to integrate, it looks like, from y equals 0 up to y equals 4. Those are, given to us as boundaries. Then we're going to be integrating, with pi r squared as our area function, this is our disk method. We're going to integrate with respect to y. So we need to change, r into, something that is in terms of y. In this case, this y equals x squared is also equivalent to the square root of y is equal to x if we take the square root of both sides. And so that's where they're getting this square root of x, or sorry, square root of y distance. And that means if we go over here, we're going to have pi times the square root of y squared dy. I'll go ahead and throw that pi out front. Let's go ahead actually and rewrite this one more time so that we get just a plain old y dy. Oh, and here's where we can integrate or, take an antiderivative. We get 1/2 y squared, 4, and 0. And yeah, when we do this, we'll have pi times 1/2 times 4 squared minus 1/2 times 0 times squared. And so 4 squared is 16, half of 16 is 8. Here we get 8 pi as the volume of this paraboloid shape. It means that we've added up the cross-sectional area of a bunch of circles from the bottom up to the top, which is pretty good. Yeah, as a highlight of what's come next, there are more problems. On this one, we'll be making another disk. Here we're oriented with dx as our line segment. This little line segment is perpendicular to the x-axis. So we're going to make a bunch of disks there. This one is going to be a washer because the axis of rotation is separated from our line segment. So we've got an inner radius and an outer radius to worry about. On this one, we could do these, I guess both ways. This is similar to the example that we started off with, but here we've got a line y equals x and then one that's y equals x squared. If we were going about the y-axis, we could use a washer method like that. If we were going about the line y equals 2, we would be rotating around something that was parallel to the x-axis, but it's still perpendicular to this line segment. So we could do it using a washer. We could totally do that using a shell method as well. But yeah, those are some more shapes that we'll do. This is another shape that we could do using the shell method. Yeah, if we had to do one, this would be a good one to do quickly. This is another shell method, so that's all good. We can totally leave some of those for the next time. We're going to talk about the arc length and calculating the length of arcs. It'll be good. We're going to learn about the arc length differential and all that kind of stuff on Monday. And I think, though, that we can, I think we can end it here. We did a good job. There we implemented the disk method. We introduced the cylindrical shell and the washer method and the area formulas that they're based on. We did a lot of good stuff with the cross-sectional area stuff too, the volume by slices. So I hope you have a great weekend. We'll see you on Monday, and we will finish this up before Thanksgiving comes. All right, we'll see ya.